Hey guys, it's me, and I'm here to talk to you about the second part of your gas law notes. Okay, so we've got a few more gas laws to learn, and then we'll be done with our unit on gases. These set of notes starts off, and it's already typed on your paper, with the ideal gas law. And I remember the ideal gas law as PIVNERT, okay? And everything stands for something that we're already kind of familiar with anyway, so super easy. P is going to be pressure, and in PIVNERT, we always want pressure to be in atmospheres. So if it is not in atmospheres, we're going to have to convert it back. So you'll use your first set of notes on gases to do that. V is volume. Volume is always going to be liters. So if I'm really mean and I give you milliliters, you're going to need to convert it. N is number of moles, okay? So if I give you grams, convert to moles, plug and chug. R is this constant number. It's 0.0821. That is not a number you have to memorize. That is a number I will give you, okay? And then T is temperature, and temperature is going to be in kelvins, okay? So we're going to go ahead and work on the example, the first one under where it says PIVNERT on your sheet of paper. The helium in a 1.5 liter flask at 25 degrees Celsius exerts a pressure of 0.6 atmospheres. How many moles of helium are there in the flask? So when I look at that problem, I see it as a PIVNERT problem. First thing I do is look for that pressure. And when you look, you find that pressure is 0.6 atmospheres. It's in atmospheres. I'm good to go, so I can just plug that in. Volume in liters. I'm searching the whole problem, and I see 1.5 liters. So I can put that in for volume. Number of moles. That's what I'm looking for. So that becomes my X. R is always this weird number. So I just put it in there. And then the temperature I gave you is 25 degrees Celsius. And you know already that all of our gas stuff has to be in kelvins. So I'm going to add 273 to that. And I get 298 Kelvin. Okay? Now, because you're also super math students, you should know that you're going to multiply these, divide by these, and you should get an answer that is somewhere around 0.04 moles. Okay? Second example, and I'm going to do that one. Here, I'll do that one in a different color, okay? 56 grams of nitrogen occupies 0.5 liters and 101 degrees Celsius. What is the pressure? Now, on this one, I gave you grams, and right away, there is a red flag going on in my super chemist mind because I know I have to have moles. So the very first thing you want to do is take that 56 grams of nitrogen, and you're going to want to convert that to moles. And that's easy. That's a two-stepper. Grams to moles. Moles gets 1. Grams comes from the periodic table. Nitrogen is 14. But there's 2 of them there. So that's going to be 28. And when I plug and chug that in my calculator, I find out that I have 2 moles. Now I'm ready to plug and chug into my equation. All right, so the pressure is not given. So this time pressure is going to be X. Volume is 0.5 liters, so I put that in, and I'm in liters, so I'm good to go. Moles is what I just found, so I put that in. R is my weird number. And the temperature is 101. That's in degrees Celsius, so I have to add 273. And now all I'm doing is my Algebra 1 stuff. I'm just solving for X. So I'm going to multiply everything on this side, and I'm going to divide by this number. And I end up with a lot of pressure, 123-ish atmospheres. Okay, and remember that right now I'm feeling about 1 atmosphere of pressure on me. So That's a lot of pressure, okay? That is the ideal gas law. The next gas law in your notes is Dalton's law of partial pressure, and these are the super easy gas laws. These are the ones you're going to want me to put on your test and quiz, because Dalton, all he said was, if I have 5 gases in a container and I want to know the pressure inside the container, I add up the pressure of those gases. How easy is that? So if you look at the first example under Dalton's law of partial pressure, determine the total pressure of a gas mixture that contains oxygen, nitrogen, and helium. And then it gives you the partial pressures. So basically, Dalton said, if I want to find the total pressure, I've got to add up the pressure of the oxygen plus the pressure of the nitrogen plus the pressure of the helium. Easy peasy lemon squeezy. So the pressure of the oxygen is 20.0. The pressure of the nitrogen is 46.7. And the pressure of the helium is 26.7. Oopsie, let me put my little decimal there. Okay? So all I do is plug that into my calculator. My final answer, there you go. Again, these are the easy peasies. These are the ones you want me to put on your test or quiz. All right, let's do one more example and then we'll move on. The next example, air contains oxygen, nitrogen, carbon dioxide, and trace amounts. Okay, so P total, oopsie daisy, is going to equal the pressure of the oxygen, the pressure of the nitrogen, the pressure of the carbon dioxide, and the pressure of the other stuff, okay? And then if you look there, it says, what is the partial pressure of oxygen? Oh my goodness, my X has shifted. So that's going to become my X. If the total pressure is 101.3, okay, so there's the total pressure, and the pressure of the nitrogen is 79.10. The carbon dioxide is 0.04, and the other stuff is 0.97. All right, taking it back to Algebra 1 a few years ago, we're going to solve for X by adding all of this up and subtracting it from that number. And you should get something around 21.2. All right, and that's Dalton's law of partial pressure. Again, super easy for super chemists. All right, now I am flippy poo-pooing the page over, okay? And we have one more gas law to talk about, and that's Graham's law of effusion. All righty, poo. So, effusion, I know in biology, a lot of times you talk about diffusion. Like if I spray some perfume here, it diffuses across the room, and eventually you can smell it on the other side of the room faintly. Effusion is different. Effusion is when you have a tiny hole or a porous substance. But think tiny hole, and gases fly through it. And the deal is, the lighter the gas, the faster it flies through that hole. So if I have a big balloon full of different gases and I pop it with a pin, the lighter gases fly out of the hole quicker. Here's a track analogy. When I'm making a relay team for track and I'm looking for some sprinters, I'm usually looking for some trim people. I usually don't put biggie 500-pounder on my relay team. Just like people, the lighter you are usually, the faster you fly. Okay? And so, effusion is just gas going through that tiny hole. The lighter you are, the faster. And by lighter, I mean the lower the mass. So when you look on that periodic table, whoever has the smallest mass is going to effuse or move faster. So looking at your sheet, it says, what effuses faster, hydrogen or chlorine? Well, when you look at the periodic table, hydrogen has a smaller mass. So hydrogen is going to fly through that hole quicker, all right? Now, Graham's law of effusion also has a mathy poo side, okay? And his little law looks like this. MM is going to stand for molar mass, just adding the mass up on the periodic table. What is a little confusing about Graham's Law? There's a couple of things that give people the heebie-jeebies. You got a square root sign. Just embrace it and love up on it. Square roots need love too, okay? The other thing is, whatever this substance is up here, its molar mass is diagonally across from it. It's the same thing here, B and B. So when I read an example, I physically write out who I'm going to make A and who I'm going to make B just to double check myself. So if you look at the example on your paper, an oxygen molecule travels at 480, that's meters per second, at room temperature. How fast would a molecule of sulfur trioxide travel at the same temperature? Okay, so I'm going to say that A is oxygen and B is sulfur trioxide. And I know it might be a little bit of extra work to write that there, but it'll keep you straight in the long run, okay? So rate A. How fast is oxygen going? It's going 480, okay? Rate B. How fast is this going? Well, shucky darn and slop the chickens, I don't know. So that becomes my X. Molar mass B. What is the mass of this on the periodic table? So sulfur is 32 plus 3 oxygens at 16. That's 80. Okay? Molar mass A. A is oxygen. Oxygen is 16. There's 2 of them. 16 plus 16 is 32. All right? Now, I'm going to simplify this. This is how I would do it. Okay? I would say 480 over X equals the square root of 80 divided by 32. And I'm going to cheat because I've already done this. So I'm going to simplify it to look like that. Okay? Then I'm going to simplify it again. And I'm going to have 480 over X. And I'm going to find the square root of 2.5 in my calculator, which is 1.58. And now I can solve for X. Now, yes, X is in the denominator, but that's okay. If that bothers you when you're going to solve, you should take this number and put it over 1. Because if you put it over 1, do you really change a number? No. And then you can just cross multiply. I'm trying to find something that'll show up for you guys. There we go. All right. So now I have 480 times 1 equals 480, right? 1.58 times X, 1.58X. And remember from math class, whatever number is by the X goes on the bottom. That's what you divide by, right? So 480 divided by 1.58 equals 304, and I'm done. Now, the only other thing that sometimes people have the heebie-jeebies about is if there is an X under a square root sign. If you have an X under the square root, you square everything in the problem to get it out, okay? And if you have questions about the math behind that, you need to ask me in class, okay? I hope this was helpful. I can't wait to see you guys in class. Take care.